So good morning, everybody. Thanks for coming to, can everyone hear me okay? I don't think, yeah. Not loud, but you can hear me. It's a pretty small room, yeah. So thanks for coming. There's no juggling in here, and my job is only to introduce the speakers, not to give you any elaborate tricks. And it's my pleasure to introduce Radu Pop from Modeline, and he's going to give us a wonderful talk about graphs and Elasticsearch.
Thank you, Nate. Can you hear me? Okay. So, good morning, everyone. I'm glad you joined me for this session, this early morning session after a nice, excellent dinner organized by iStack committee. Thanks for organizing this fantastic event. And after a bonus of juggling session yesterday, so I have seen lots of exciting and very interesting use cases yesterday about different use cases, mostly e-commerce, but not only. Also in MICE's event the day before yesterday. So I was willing to give you different use cases in my talk. I hope it will be interesting for you because it gives a different perspective, a different viewpoint on the data. So searching through large graphs using Elasticsearch. I would take just a short time to introduce myself. So my name is Radu Pop. My role is solution architect at Adlin team. My areas of interest cover mostly Elasticsearch stack, but also enterprise search solution that we call it A2 search. So I've been in charge of evolving this product and integrating it in several cases. And of course, relevance, it's one of the areas that it's very interesting for me. But I have to mention the second hat that I will wear today, which it's a role of search consultant in an institute called National Institute of Audio and Visual in France. My main interest in this project is the Elasticsearch search engine, the implementation of a search engine based on Elasticsearch, and this is part of a project called Data Lake. So I will just give you a short introduction about this use case and about the institute. Because it's interesting and it will explain later on why there are some specificities and some particularities that makes it interesting for a search engine, and there are some challenges that we went through in this adventure. So the institute, we see it as a very large repository. It holds more than 180 radio and television services, which are regularly archived 24/7 since 1995. So you can imagine this generates lots of data, lots of content. They are, just to give a short list of figures, more than 22 million hours archived. That generates more than 1,100 billion views on different websites of the institute. So different people or different other institutions can access this content. There are also lots of photos, lots of official photos and archived photos, more than 1.2 millions. And there is also a website archive getting to more than 4 petabytes of content. So I just put this image on the right side of the screen because I find it the most relevant in illustrating the institute as a long corridor of drawers and shelves with lots of tapes and of course, this is the legacy, the old fashion of storing, archiving cultural heritage in France. Now we have lots of racks of computers, but the idea is the same. So lots of data. So of course, there are different activities. I don't want to get into more details. It's a large institute with different training sessions and curating and analyzing teams. The project that I joined is it's called the Data Lake, and basically its role is to host these documents. So all these over 50 million documents that describe all this audiovisual content. And it operates like a typical three-tier architecture, right? So we have a storage system of different databases, legacy databases, recent. So it's a very heterogeneous environment of storage. There is also the processing to update, to transform, to curate, to synchronize different sources of data. So there are different teams and different experts involved in this area. And also, so the third layer is the management of this data, access, monitor, and what's interesting for me and my role is on the search part. I wanted to give credit to the team, Gauthier, Colin, and Stanislas. They are the people, the core of the team. They are there for several years already, but of course there are some other collaborators in different parts of the project. Now, strictly related to the project, what it's important to introduce is the data model, because it's not just simple documents that metadata that describe some items, and then we just index them, and then we search based on keywords. Actually, what is very important to dissociate is these three viewpoints on the content. So you have the content in itself, which is the video and audio. It can be news, it could be live, it could be replays, different documentaries, series, movies, everything. Even publicity is archived. Images, different official images, different personalities, different events. So, and also text, written notes, books, press releases, you name it. So this is the pure content. But this is not everything, because each content, it's also related to some events. So this a specific content happened at some point in time, and this event has its own characteristics. For instance, it could be the first broadcast of a TV show, or there are some replays, or the moment then that a movie was archived. So on different events. So this is an important point of view for the archiving and preservation perspective, because we can follow up the evolution of the content. And the third layer of this model is the support in itself, so the media. How is it, the content, how is it represented, physically represented? Is it a tape? It's a file, MP3 file? Is it a web archive? So on. So keep in mind, this is the general view of the data model. Now, when we get more into details, it's a semi-structured data model. So this content is described by some metadata, and it could be, as shown here, it could be some free text, different instances could have a title, a description, some notes, but also some structured information. There are some concepts that can be associated to several entities. They are descriptors, they are ontologies of different concepts, and so on. So this gives quite complex and heterogeneous view on the data model. The team had a long discussion with the professionals, and they scratched their heads and tried to come up with a global schema, an abstract view to all these relations in between different elements. So they came up with something similar to this. Again, here I simplified a bit. I didn't put all the details, but just to see that we can see that the global view of the model as a graph, right? So there are different entities with specific characteristics and different relations in between different entities. If I come back to the example of a daily news, for instance, at 8 p.m. each day you have the news on the national channel. So that's what we call an instance, right? So this instance can have relations to other instances or other group and categories of instances. For instance, a particular day of the news which is broadcasted at 8 p.m. It can have a replay the next day in the morning, or it's part of a group globally defined as news. Then there is a list of events that are associated to this, and then lots of other entities like the credit. We have different people that are presented in this news. There are relations to several concepts, and then each instance has a text, title, so on. So there are very complex relations in between all these entities. And now the challenge is to be able to transpose this model and to instantiate this model. First of all, we have a relational database. So behind all these elements, they are stored in a database. Of course, with all these complex relations in between the entities. But also, if we want to index and be able to build a search engine on top of this, we need to have also a document view associated to this model. So this is the first challenge that we had to tackle with. So how do we do this transposition of this graph into documents? And when I say documents, it's flat documents, because more complexity, you add more joins and more dependencies and relations in between sub-elements of documents, more difficult it becomes while searching. So the simplest idea is to try to cut this graph, right? Instead of putting everything all together and computing all the extracting all the relations in between all the elements, all the rows in the database, you just decide of a simplified view on the graph. And for instance, if I want to have an index of concepts, so all the concepts that describe different content that I have, I just choose the concept elements, I choose concept schemes, the texts that are related, so I will index all that in a dedicated index which stores the concepts. The same thing if I want to enlarge my view. I want to be able to browse and search through all the video content and broadcasted shows with a title and with different occurrences. So I will generate an instance index, and so on. For events, the same thing. I would just decide another cut in the graph, So this way, my documents will be simplified. Now, of course, this choice is not done randomly. This is the result of different discussions with the specialist, with the business holders, and it was decided to include or to exclude some of the elements according to their importance and their needs in searching afterwards. So that was the first challenge that we had to address. So now, how do we index these documents? What's the workflow? The key question was how to treat this heterogeneity of the original data. Here I'm just showing different databases. Sometimes they are legacy databases, and they need some curating, some migration to the more recent way to structure the data. So this is a mandatory step before considering a final indexing into a search engine. So this is done in a Postgres database, which has the objective to gather everything. So it's a very large relational database. And then in the preliminary part of the project, we were thinking, okay, so we have all the data in a relational database. All we need to do is just take one by one. We follow the different choices of cutting the graph and organizing into smaller documents and choosing a limited number of relations. And we index JSON documents in Elasticsearch, and that's it. So we did that, and considering the volume of data, the whole process took about 2 or 3 weeks. So we thought, okay, we managed to index everything, but this is not acceptable because we would need to do updates. From time to time, there will be some new content to be added or some migration process to be performed. So then the second challenge was to be able to find a way of reducing the indexing time. So that was a mandatory aspect. And that's why we introduced an intermediary step, a preliminary step of indexing process, where we used a document database, a MongoDB, and we indexed not the final documents, but something that we called JSON fragments. And I'll come later on with some insights about these fragments. So to summarize, on the PostgreSQL database, we have some optimized SQL queries to be able to deal with the heterogeneity of different databases. And on the pre-processing phase in MongoDB, we used some JSON fragments based on specific schemas. So the document, the representation of our data from the relational view passing through the fragments, which basically define schemas and relation in between different elements. So for instance, here we are talking about an instance, and related to this instance, we chose only text identifiers, concept events, and archive group aggregation. So this is the list, a limited list of relations with other entities that we want to extract. So we won't take everything from the relational schema, but we only select these parts. So the result is what? It's a JSON document, rather flat, with not so many imbricated and not so many level in different parts, different textual parts of the document. We have the the essential characteristic of an instance, like the media type, what category of document, different hierarchical place into the ontology. We have in the list of texts, of course, everything is identified by IDs, and these are not technical IDs, they are rather functional IDs, and the curators and the practitioners are very keen on following up on different IDs of specific elements, specific text. This is, for instance, the name of a video fragment, which was first published in 1987, and which is part of a collection that has the same name, which gathers several documents related to this one. So this is the result of using a fragment and choosing, having a selective way of integrating data. So a bit more details on the JSON fragment. It's inspired from JQL. We studied a bit, and we decided to have our own implementation to be able to have more flexibility in defining the schemas. It's a declarative method for the structure of the documents, because this is what we define for each category of entities. So here I'm talking about instances, but there's another schema for events, another schema for concepts, and so on. So we have the flexibility of defining new schemas. Even if there are new needs in the future, we can simply change, add things, or remove things from the schema, and the mechanism behind will function normally. And then if I unfold these different sub-elements of the schema, you can see that we can imbricate several relations. And here, just to simplify, I added just the text and the identifiers. So basically, using the schema, we extract from the relational databases only these elements that are interesting in this view. A simple example, I won't get into all the details, but just to see that from a simple schema of 10, 15 lines, we can have a very detailed information and quite large document of 80 lines, when we can extract all the necessary parts that will be indexed in the search engine. And this is, of course, with some quite elaborate SQL queries, which explains why it takes quite a lot of time to generate all that and to index into Elasticsearch. So this was not the bottleneck of the indexing process. It was not the search engine. It was not the Elasticsearch cluster, but rather the complexity of extracting all these relations. So what we did in order to implement these schemas and a transformation on the fly of the data, we used a library called GSLT, which is an open source library. Anyone heard or used GSLT already? Okay, so it's a query and transformation language for JSON, inspired by JQ XPath XQuery. It's simple and very fast, actually. I would say it's much easier than a full programming language. Of course, we can do these kind of transformations using Java or Python or whatever we want, but it's much simpler in JSON because somehow it's declarative. You don't have to write code or to build and to deploy different specific processing units. It works on the fly, and it has the effect of transforming very easily complex JSON documents. Moreover, as we needed these transformations for different cases, we were able to build a set of small modules or extensions of this library that is reusable and off-the-shelf tools that allowed us to easily transform the documents. For instance, what are the main transformations? It was, first of all, to flatten the fragments that we obtained. So here, for instance, you have different relation types, different types of text with different IDs, values, different languages in French, in English, and so on. And then the result of a simple transformation of all this verbose content, it's something much simpler, compact, and that it's easy to index afterwards in the search engine. Just to have a glimpse on what JSLT looks like, so you have simple loops, you have declarative functions, or you can add elements, key values, you can add different elements that are computed by other methods, and so on. So the language in itself, it's quite simple with a very powerful effect. So that filled in our purpose, our goal to easily transform documents. Now, as we have the documents, the next challenge was to be able to index them in all these different indices. So we wanted to have a generic and consistent way of processing these transformations and these indexing tasks. So this is just to picture different indices that we have. We have an index of events, concepts, agents, and so on. And each one is based on a first step of identifying the list of elements that will be indexed into the final index. And then there is the transformation process that will be plugged on this indexing job. So there is a variety of jobs that are part of our platform. They are triggered synchronously or asynchronously, either by direct web service calls, or there is an AMQP message queue that can keep the track of different transformations that are systematically triggered. And all these jobs are just generic jobs that will function with a small change of parameters or different values of parameters to adapt them to specific indices. It's a declarative definition of these jobs, which simply based on configuration file, which reduces the maintenance effort. We don't have to redefine a new job or to have specific jobs for specific indices. And we can orchestrate these jobs with a framework that we chose. It's about talent framework. Of course, considering the various indexing jobs that we have to deal with, it cannot be done manually, or difficult to imagine having an in-house orchestration of these jobs. So we based our the management of the indexing process. We based on this talent framework that offers also the possibility to have a console. That's a screenshot of a simple example as creating an index, for instance. It can be scheduled. We can pass a certain list of parameters, like the name of the Elasticsearch alias, the timestamp, the endpoint, and so on. So just to illustrate that in just a couple of clicks, you can define and you can orchestrate generic jobs. You can activate, deactivate, and so on. Another facility of Talend framework is that you have graphical interface to define the job. So no need of coding and writing code to for specific parts of the process. Here, for instance, it's an asynchronous job for reading from the message queue, setting up a certain specific parameters in the beginning of the job, checking the Elasticsearch status if we want to create a new index, to prepare it more precisely, to associate the correct mapping, associate the correct settings, and so on. And then when the previous treatment generated a list of elements to index, there is a bulk sub-process here that will go through the list of elements and check the status and validate the indexing. So this is just to illustrate the indexing process using Talend framework. Now, up to here, I was only talking about the indexing because it was an important step and lots of key points to tackle. But it's also the search that we put in place. It's a simplified search API that provides a standardized view on different applications that are accessing the search engine. It preserves also an abstract level of Elastic Query DSL, so no need to be expert in Elasticsearch and no need to know the complexity behind. The application will have simple facilities like text search, filters, facet, sort. And another important point is that these APIs allow us to confine and control the access to the Elasticsearch cluster, because this is a key point considering that the application potentially access a large volume of data and could trigger, for instance, very large computation of facets or imbricated aggregations, and that could eventually lead to an out-of-memory error on a specific client client node in the cluster. So all that, we wrapped all that in our search APIs. And also they are designed according to the functional needs. Some applications, they only need a list of documents by ID. Some others, they need full text search. Some other need only an autocomplete. So that allows to define a specific functionality based on the functional level. We also used GSLT transformation to generate these queries. And just to take an example here, for a simple query on the left that is generated by the application, so they only have to specify the text, a filter, for instance, a facet, and, for instance, a facet on different events, different elements of persons that are related to these events, some simple rules of sorting. And so for a simple 20 lines query, the transformation, it's something like this. On the right side, we are getting to hundreds of lines of Elasticsearch query. So this is just to illustrate the facility of adopting the APIs for the application level, and also the complexity that we can add using different complex structures like nested or different aggregations in Elasticsearch. Just a short grasp on the different modules that we used in GSLT to implement all that. We can have a simple function that defines the sorts, a simple function to define the list of facets available, and then the query is generated directly on the fly. You have the from size query. All the JSON elements in the query are explicitly specified in the GSLT transformation. In the workflow, we have a preliminary query validation. So this is very useful for facilitating the paginations, for instance, selection of language. There are different documents in different language. And then it's the second step is the Elasticsearch query transformation in itself, the definition of filters. We can define different profiles associated to different users. So basically, all the complexity of building the query is it's hidden in this second step. And then what's also important is the presentation of the results, because sometimes the results are quite verbose. There are lots of informations, especially when the aggregations are on different levels and they cover larger ontologies. It's useful to have a transformation and the presentation of the data more adapted to the application. That leads me to a couple of words about the architecture. The key word in the architecture is the modularity. So the search engine functions as simple Spring Boot applications managed on Kubernetes. The deployment of different resources and configuration is very easy because we are talking about GSLT files that are just deployed on an instance, and they are on the fly reloaded or modified, so no need to build or do complicated deployment cycles. There is a Elasticsearch cluster on-premise that is accessed only by the search engine and controlled by a proxy, where we specifically define different access rules and different endpoints that are available for the application layer. Two words about the evaluation. I was mentioning that in a preliminary phase, we had a very long phase of in the order of weeks of processing, and then using the JSON fragments, we managed to index the totality of 50 million documents in less than 48 hours, which is somehow reasonable and acceptable from the point of view of the stakeholders, because a full reindex of all the documents doesn't, we want a core each and every month, or maybe it's only triggered by different curators curating processes. So these fragment optimizations allowed us to divide basically by 10 the global processing time. And we measured a bit the search performance, because that's also important, considering that some queries could be quite complex. The curators sometimes are interested in going, in drilling deep into the whole ontology of concepts and to retrieve all the events or all the entities related to a specific concept. So that leads to very large aggregations and imbricated aggregations on 4, 5, 6 levels of imbrication. So we wanted to try all that and to see how the cluster will perform. we used the Neoload platform, which is a platform shared by different other projects in the institute. And in terms of response time, we had less than 200 milliseconds in average for average complexity of the query. And this is somehow acceptable because we are not in the case of a website where the constraints are harder. Here, users are, they know that their queries are complex, and they will browse through the global data set in the lake. So we consider that responding time below 200 milliseconds was reasonable. Just a snapshot on the evaluation process that we performed on Neoload platform. We started with 10 or 100 users, concurrent users, and we increased each and every 2 minutes up to 400 users. And what's interesting to notice is that the response time increased a bit, but in a stable manner. So basically, that validated our configuration. That these scenarios helped us to validate the configuration of the cluster and also the complexity of the query. So if ever we had some issues or some parts of complex query, that would be they would have been shown in this evaluation. Just to wrap up, there are 5 takeaways that I would like you to retain. So these ones, they correspond to different challenges that we had in our project. I would say our project is it's like a puzzle. So several small or not so small challenges, some solutions that we had to implement from different steps. So the first one to start with is the choice of the data model, the entities graph. And the key question is how to flatten the graph, so based on functional views. And the second key point is the usage of the fragments, so introducing a pre-processing stage in the indexing process that allowed us to drastically reduce the global processing time. The third point, the usage of GSLT transformations, because that helps in the document normalization and also on the side of the query implementation, being able to simplify the search API. And the last but not the least is the search relevance, because, and that's why I'm here, we started the works of improving the relevance, but at this stage it's not very complex and it's not very elaborate, and this is what we are looking forward to develop in the near future. So that's it. Thank you for listening. And if you have time, and if you have any questions.
Can you guys hear me? Yeah. So we started 5 minutes late. I'm going to give 2-3 minutes for questions. Does anyone have anything in the room? And I'll run up and deliver the mic. Yep.
Hi, thank you. Just looking at the number of transformations that is going from the relational view to the search view, how, and this is a catalog that's being continuously updated by curators, right? So how many rules or triggers, or what was the mechanism by which you propagate the updates across the views?
That's a very good question. And the updates are one of the most challenging part, because what happens when there is an update on a very generic entity, it will have an impact on potentially thousands or millions of other entities. So actually what we did, we used the same scenario of defining fragments, if you want. So for each update scenario, we associated a list of checks, a list of validations and updates that are triggered by the first operation. And we propagate all these updates up to the last level of the dependence, the relations in between different elements. And of course, depending on the type of entity that generates more or less updates into the final documents in Elasticsearch. And to implement all that, we reuse the same mechanism of jobs, asynchronous jobs that are triggered and scheduled in a queue, and then they will be continuously treated along the way.
Thanks for the answer, Radu. I think we're at about time. If you guys have further questions, let's follow up in the lobby outside. But we have 10 minutes until our next talk. I hope to see everyone back in here. And thanks for coming to the first one. And let's give Radu a round of applause for thanking him again.